anyways, let's move on. We're on quantum computing part 4 again. If you want to follow along with my notes, they're on Discord. We're on last time. Let's talk about quantum circuits. Last time we talked about quantum circuits. Quantum circuits, circuits, and quantum circuits. Let's see. We had a couple examples. Let's just do the one main example we did, which was like what are they good for? What can you do with it? And one of the things you could do is write. So like, here's a common circuit. What do we got? GCB, thank you for the follow. Welcome to the community. I wish I could answer some of those questions. So what did we say this was? Like, we went through the whole process last week. We just drew this little circuit, and the circuits are like any Feynman diagrams. They're just pictures that represent equations, right? And we did a truth table last week. We did the ins and outs, and found out that it's really just hidden, but it's a swap gate, right? That's all this is. We did this calculation last week via in and out table. And I guess maybe that's what Rooster was asking about doing that type of logic versus computational stuff. But to me, honestly, I don't know. It feels the same. But I think that's an interesting question to ask. It's kind of fun. I kind of like it. It's like more of like a puzzle, than an actual like, what's the other word? What's not a puzzle? I don't know. Rigor. So it's kind of fun. But yeah, so if you take 3C NOT gates, this is just, again, a useful application. 3C NOT gates is actually just one swap gate. So that's kind of cool to know, too. And then last time else we talked about is qubit copying. We asked if you could copy a qubit. And the answer was absolutely not. There is no qubit copying in quantum mechanics, in quantum computing. I remember the fun one, drive G is a constant. I might have, I don't know, maybe I've even seen that one. But I certainly couldn't do it off the top of my head. Does qubit have a Q? Yes. Oh no. I wrote it that way in my notes too. Oh man. Good catch. Good catch. That's funny. Okay. And so the no cloning theorem. So we called this the no cloning theorem, very popular in quantum information and trying to understand quantum information inside of black holes. No cloning theorem. That, I don't know how that works. And we also talked, so the no cloning theorem. We showed the little bit of math for that, which was if you had, two psi's, where psi is given as is a times 0 plus b times 1. And then if you were to write psi, then it was a times the state 0, 0, a squared, times the state 0, 0, plus ab times the state 0, 1, plus ab times the state 1, 0, plus b squared times the state 1, 1. And then we found out that the only way that this works is if a or b is equal to 0. And then this is obviously not true, so we couldn't compute our we couldn't copy our information. Okay. And then lastly, we talked about quantum teleportation, which was, of course, relevant in this PBS Spacetime video we watched, and some other things that we talked about today. So if you're interested in those things, quantum teleportation, so spooky, go ahead and give the old VOD a watch. Now, we're on to quantum algorithms. Quantum algorithms. And the question again was posed, can we do classical computations on a quantum computer? Well, the answer is yes. Actually, that just kidding in my notes doesn't really make sense. The answer is yes. Undoubtedly yes. We can get reversibility. Like, reversibility is one of those things where, like, we needed circuits and gates to be reversible. But that's not necessarily something that's inherent in a classical computer. That's just sort of something that happens, right? So can we do these classical calculations using reversible computers? Okay, fine. Or can we do the classical computations using a reversible gate? And it turns out we can. And that is called the Toffoli gate. So the Toffoli gate has this circuit diagram. It's now a 3-qubit gate where we have 2 controls and 1 target. See, I'm getting good at this language now. We have 2 controls and 1 target, and it's basically exactly what you'd expect for the controls. So let's do a truth table for this. So we have 3 qubits, A, B, C, A prime, B prime, C prime, and those are going to be our ins and our outs. So our ins, so it's going to be exactly what we did for the C0 gate, except instead of having 1 control, there's just 2. So now we're going to be looking for when A and B are going to be the value 1 instead of the value 0, and then it's going to flip the 3rd qubit. So as you can imagine, all of these first ones aren't going to do anything, so we'll have 0, 0, 0 is just going to get 0, 0, 0, 0, 0, 1 is going to get 0, 0, 1, and we can just go down the line. It's in the notes, and it won't really matter all the way until you get to the final 2. We have 1, 1, 0. That's gonna, the first two bits are 1. So this would look like state A, state B, and state C. And then this is just gonna be state A prime, B prime, C prime. And yeah, so the first 2 bits, if they're both 1, they're gonna flip the C bit. That's what this is. So if 1 hit this will flip. So this is going to be 1, 1, 1. And then likewise, if we have 1, 1, 1, then it's going to flip the C bit again. And it will look like that, okay? So you can write out the whole truth table, but again, it's just going to be the different permutations of 0s and 1s through these 3 variables, or these 3 qubits. Now, the Toffoli gate is useful because, and I don't know how, so I'm not going to bother with it, but you can do it yourself. You can actually simulate the NAND gates and the fan-out gates. And those are the ones that you need in order to recreate a classical computation. So fan-out and NAND gates are the ones that you were interested in for classical computation. And again, not 100% sure. What do they look like? Can we draw the diagrams really quickly? Well, sure. It's just going to be variations of the Toffoli gate. So there's 2 of them, really, the NAND and the fan-out. And then again, this is you guys being able... I'm not very proficient with the quantum or the classical computations and logic gates and stuff, so, but I know a lot of you are, so you might want to see it. And the basically looks like this. One thing about the Toffoli gate while I'm drawing these is it is an 8x8 matrix because we have 3 tensored qubits together. So that's 2 to the 3rd, which is 8. So there's our first one, and there's our second one. Woo, woo, woo. Ta-ta-ta, ta-ta-ta-ta-ta. And this is again, now we have A, B, and C. Weird. Hold on just a second. Okay, what do we got? Yeah. Scrape Crow, welcome to the channel. Thank you for the follow. If you have any questions, there's instructions right there. Okay, so now if A and B, this is basically fancy language for saying if A and B are 1, then this is going to flip because it's a modulus 2. So if they're 1, then 1 plus 1 is 2, so modulus 2 is going to be 0, so this 1 will flip to 0. Otherwise, it's just going to be 1. Now, that's the NAND gate. And then if you wanted to talk about the fan-out gate, again, this is for those who are interested in classical computing. This would take 1 to 1. Okay, so now we know that this control is always going to be hit. Then you have A to A, so this is the control that will be flippy floppy, and this is going to be 0, but this is going to be A, right? Because if this is 0, then you're not going to flip this. So again, 0, 0, so 0, 0, perfect. And if this is 1, then the control is going to hit and flip this one from 0 to 1, so this is going to be 1. So if 1, 1, good. Okay? So that's how those two work, and that's how you Easton, welcome, welcome, welcome. That's how you can simulate classical computations using the Toffoli gate, okay? All right, let's get rid of all this classical mumbo jumbo. Because this time, I guess today's lesson's kind of short because I'm already done with the first two pages. Okay, so we have 2 more pages, but that's probably pretty much it. So let's get rid of all this classical computation mumbo jumbo. You're not here to learn about classical computation. You want to know what makes a quantum algorithm different. Why is it special? Right? What? Oh, wait, rid of that too. What can you tell me about quantum computing that I can't do to classical computing? And then everybody's always response is, well, you can do parallel calculations. Well, what does a parallel calculation even mean? You know? Like, this is the thing we want to know. Doesn't this violate the no cloning theory? Fan out, that is? No, because you're making a sacrifice for the, like, I know last time we talked about that the no cloning theorem got that. But it's okay if you're making a sacrifice. Like, I'll give you the example. I'm not 100% sure about how this doesn't. Unless A has to be a bit. Like a qubit, or a classical qubit. You know what I'm saying? When I say classical qubit, you know what I mean? Like it has to be a 0 or a 1. Like it can't be a superposition of states. Does that make sense? It can't be a superposition, I think. Maybe that's the trick. I don't remember 100% on what the trick is for the Toffoli gate, but from the other perspective, the reason we were able to do the quantum teleportation, we didn't take the psi qubit and then give it to Bob, and we didn't clone it and then pass it from. We didn't clone it to Bob's. Instead, we sacrificed Alice's entangled bit. So we kind of sacrificed the 1 qubit, which was psi. Plus Alice's qubit, we'll call it A, was able to shift, Bob's qubit to psi. I'm just writing down the way that it worked. So these 2 things combined was what happened where we got Bob's qubit to psi. But we didn't when we applied the Hadamard gate to this, we actually ended up getting it out of psi and it became like a psi prime of some kind. And then we were able to measure these, and that caused this to go into this state. So that was kind of the outline of what we had happen. So we got psi from here to here, but we didn't clone it. Instead, we ended up manipulating it, and then Bob had no choice but to be able to figure out what psi was on purpose. So hopefully that mumbo jumbo picture helped that question. Where does quantum come from? Actually, I don't know. That's a great question. Where does the name quantum come from? Does anyone know the history on the word quantum? Is it like Latin for something? So putting something in an unknown but measurable quantum position is legal as long as you destroy some other quantum state. Yes, exactly. Yep. Like you can't just make you can't just take a psi state. What do? We had like a psi and like a 0 state. And the question is, can we turn this into psi? And that's a big no. Like this was a big no. But we took psi. Basically what we did was we took psi and then an A and a B, and we turned this into like a psi prime, an A, and then a psi. But we had to do something to this in order to get this psi. The Hadamard gate was really switching bases from psi to a different psi, and then we could take a measurement, and that was what transferred psi. Yeah. Like a photon is a quantum of E and M. Yeah, but what does the word quantum mean? In 1901, Max Planck used quanta to mean quanta of light. But does it have that's where the origins of the quanta came from. From the tiny bit of Latin grammar I know, quantum is the singular of quanta. Quanta or quant count. So small but countable? Is that what that means? Discrete. Ooh, maybe it's like Latin for discrete or something. Maybe that's what it means. I got way too excited about that. From Latin, the neuter of quantus referring to quantus or quantity. So we'll call it discrete. Indivisible. There we go. That's, yeah. Haha. Yeah. Microphysics. Yeah, but then we'd just be like chemists. We have to be careful. Okay, so what are we on to now? Okay, so next up, quantum algorithm. What is it good for? And we have quantum. And this is what you've all been waiting for. I think some people literally just joined my channel months ago so that at some point I would teach them what quantum parallelism is. Can I spell it? Well, you're going to be very disappointed because it's only partially exciting. No, I'm kidding. It's actually really cool. Now, let's go over... this is, I'm going to read directly from Nielsen and Chang, and this is a good thing I do. I do this every once in a while, and it's basically because I can't say anything about this nearly as well as they can because they're the experts. So we're going to do that. Ready? It says, heuristically, at the risk of oversimplifying, quantum parallelism allows quantum computers to evaluate a function, f of x, for many different values of x simultaneously. So they are saying that that is like a definition that is... Excuse you. They are saying that it's a definition that leaves a lot to be desired. Okay? And it's simply not going to be as straightforward as one wants, right? But that it's a very practical usage of this operation, this parallelism, right? Is to understand... you can just do the calculations and understand that it does work, but there is, like they said, heuristically, at the risk of oversimplifying, f of x is being evaluated for many different values of x simultaneously. Whatever that means, very different. I love that this is on Twitch. Also, it's only a matter of time in any physics conversation before shade is thrown at chemistry. I have chemists pop in my chat all the time and throw shade at me, and then I go to their streams and I'm like, hey, what's up, friends? And then, it's shade all around, but we all love each other. So let's go over what this function is, and then we'll see how we can compute a parallel function. So we'll have some function f of x, and it basically exists from the domain of 0 to 1 to 0 to 1. It's very simple. It has a 1-bit domain and range, so it's 1-bit domain and range. I don't know what the simplifications are for domain and range, but whatever. What is this, math? I didn't agree to this. Now the question is, can we evaluate it? Evaluate it for multiple x's at a single moment of time. So let's start with the qubit system, x, y. Okay, so we have a nice qubit system, and we're going to define an operator. Okay, it's going to be the following. It's going to transform, so this is our operator. It's going to transform x, y, this 2-qubit state. Sorry, there's 2 qubits. I don't know what I said. This 2-qubit state to something else. And we want it to be x and then y modulus f of x, where this is modulus 2. Addition of modulus 2. Okay? And of course, I'm setting all this up in a certain way on purpose. So this is the idea. This is what the function does. Is it takes the state x, y to x, comma, y modulus f of modulus addition, modulo 2 addition, excuse me, with f of x. Now, here's the circuit. We're going to have the 2 qubits come in. So this is our... what do I want to do here? Yeah, I'll just hold off a second. As you can see, the circuit's in the notes, so I'm trying to see how much of this I want to write differently than the notes. And I think I'm just going to write the exact same thing as in the notes. So this is y. F of x, this is x. And this is the UF gate. And then out here, we're going to get some psi. Now, so say we have, for our x state, we have a split state. So we'll have 0 plus 1 divided by the square root of 2. I don't know why I wrote right over top of my quantum circuit. Okay, so we have this split state. Say like you can get that anyway by using a Hadamard gate, or where can you get cheap textbooks? I don't know. Maybe, I don't know. It depends on the textbooks. Graduate textbooks are pretty cheap, but undergraduate ones are not. And I'm not 100% sure the best place to get them. But maybe somebody has a website they can use, like talk about used textbooks or something like that. I know they exist. I just don't know them off the top of my head. So then if we take this y gate and we set it at 0. Okay, now remember, this is a modulus 2. A modulo addition 2. Or modulo 2 addition. Excuse me. Jeez. Math terms. And so it really depends on what x is, okay? So let's say, so we can basically say, like, you know, since this is just the x and the x exists here, that this psi state is going to be one of the following. If it's, well, it's going to simplify to the following, and that is that this state is going to be 0, comma, f of 0 plus 1, comma, f of 1. Now, how do I know that? Well, because, over the square root of 2 for the normalization factor. Well, because we have a couple things going on here, right? Y is 0. Okay, so it doesn't really matter. Hold on a second. Am I missing something here? I want to make sure I get this right. Okay, so yeah, so if y equals 0, then the second qubit is just the value of f of x, okay? Whether it's 0 or 1, because it's not going to change from modulus 2, okay? That's the point, is whatever this is turns out to be the second state, because it's not going to be changed from the modulo 2. So if f of 0 is equal to 0, good. If f of 0 is equal to 1, good. If f of 1 is equal to 0, good. If f of 1 is equal to 1, good. That doesn't matter. It's not going to change. So this is the basic. Is 1 really equals to 2? Ooh. That's a question for flammable math. So this shows us how we were able to evaluate the value of function of f of x simultaneously, right? Here we have a superposition of the value of 0 and the value of 1. And that's kind of cool, right? Like, we went from the superposition, and that maybe like this isn't, but can you reply in physics? No, not really. 1 is equal to 0 only in, I don't know. I don't know. Let me just keep going. So yeah, so we have the state 0 and f of 0 plus 1 and f of 1, and this is now a superposition of this function. So it's basically like we're calculating both of those at the same time, right? And that's kind of what the parallelism is for, and it's nice. So this procedure can be generalized by expanding the n qubits into n Hadamard gates. So I'm not going to go over too much of the linguistics, or of the, not the linguistics, of the, to write down the different functions, because they're not, I didn't really find them too dramatically helpful. But we will do a big example, which everything should be pretty clear. So, for example, if we wanted to do 2 qubits being put into Hadamard gates, then we would get one of the following, right? Well, let's first draw our diagram. We'll have 2 qubits, 2 Hadamard gates, good, good, good. And then we could get something where we get entanglement in some sense, right? Where we get a nice arrangement of a large state. We'll have 1 over root 2 times 0 plus 1. If we start, I'm sorry, this is very particular to starting with 2 zeros, right? Because the Hadamard affects the 0 and 1 state differently. So then we'll have 1 over root 2 times 0 plus 1, 1 over root 2 times, you know, the state 0 plus the state 1. And then we could rewrite this even as, you know, 1/2 out in front of 0, 0 plus 0, 1 plus, and have all the tensored states together. 1, 0 plus 1, 1. Okay, this is not too unfamiliar to anybody. This is just having a bunch of different states. Alistar, are you looking to explain wave collapse and simultaneous uncollapse? No. The only thing that's simultaneous is about putting through multiple pieces of information. You're basically like taking a function and you're making it like kind of into quantum information and then evaluating all of those simultaneously. You can't really do explain wave collapse and simultaneously uncollapse. No. Yeah, I'm not 100% sure I understand the context for that. But let's keep going with this. Weirdly enough, simultaneity does exist in quantum mechanics as far as we know. That's the problem. That's not the solution. The solution is that it probably shouldn't. If you were to ask me. But we do evaluate things like this in a simultaneous fashion. Now, this is so this is cool, this is interesting, but it doesn't actually get to like a real calculation. So let's do what's called Deutsche's algorithm, and that's by David Deutsch, the famous quantum computing person. I'm going to draw the circuit first, and then we're going to start evaluating it. Now, I decided to do this example out. If you are following along with Nielsen and Chang, they don't go into the details. We are going to do the details and actually go over this calculation. It actually cost me, like, I had to sit there and stare at it for like a half an hour before everything started to make sense. But it makes sense now, so we're going to go over it, and hopefully my notes lead me and I don't become too far astray. So we're going to start with a 0 and a 1 state. So we're going to enter into the quantum computer, and we're going to hit 2 Hadamard gates, okay? So just like we have over there, 2 Hadamard gates. And then we're going to send these two into our UF transformation, where we have Y here and Y modulo 2 addition with F. And that's just an F. F of X. It's all F of X. X, X. And then we're going to send the last, the X gate through the Hadamard gate. And this is just going to come out. Okay? Now the goal is, so we're going to have the different states here. We'll have the 0 state here. And then here we're going to have psi of 1. And then here we'll have psi of 2. And then here we'll have psi of 3. Okay, so here's our circuit for the problem. So let's kind of go over what's going on with this. So Deutsche's algorithm combines 2 things. It combines quantum parallelism that we talked about with interference, because, you know, everything is waves and the wave collapse and blah, blah, blah. AWR417H, thank you for the follow. Welcome to the channel. So the question is, what can we do with this wave behavior? Can we do something? And David Deutsch was really, really bright. And I think that's good. Let's keep moving on. We got, so Deutsche's algorithm combines this quantum parallelism with interference. So we have the 0 state. Let's just, I mean, this one's pretty straightforward. The 0 state is 0, 1. It's 2 tensored, 2 qubits together. They're tensored. It's classical. It's no big deal. Okay? This is, yeah, you're no big deal right here. You're no big deal. Now we're going to send it through 2 Hadamard gates, and then it gets a bit spicier. Okay? So we'll have psi 1 is going to go, and we'll get, you know, a state of 0 plus 1 divided by root 2. Now remember, I said Hadamard gates affects 0 and 1 differently, so this one's going to be the other version of that, which is 0 minus the 1 state. Again, this would have been the second part of quantum mechanics. This is quantum computation part 4, and the second quantum mechanics discussion series, we talked about Hadamard gates and the different way that they behave. So this is what we'd get. So the 0 state goes to 0 plus 1 over root 2, and then the 1 state, 0 minus 1 over root 2. So then, now if we look at the transformation. So just imagine this transformation, okay? Just imagine. Just imagine for a second. What does a transformation look like if we want to apply it to some state out front we'll call X? So this state is just X. It doesn't have to be, it can be this. It can be this whole thing. But right now we're just talking about the state X, okay? What happens if it acts on the state X and the 1 over root 2 times 0 state minus 1? So basically the other state. What do we get? And that's the question we really need to ask ourselves, okay? So we know a little bit about modulo 2 addition. We can set up a truth table again, but this time let's not set up a truth table. Let's sort of set up another different type of table. And this rooster, I will say, was a lot of fun. So, but it was difficult, which sometimes equates to fun. So we know that the second side of this, right, this is going to take it to, let's just go down here. This is going to transform, I just hit my microphone, so hopefully everything's okay with sound. Yeah, okay, cool. So this is the, this is what we're going to end up getting, and that is, where'd it go? I lost my spot. Oh yeah, so then this is going to transform into the X state times the 1 over square root of 2, and then it's going to be, man, I keep losing it. Oh yeah, so the states 0, nope, still inside the state, plus modulus 2 f of x minus 1 modulus 2 f of x. Okay, so there we go. So this is what's going to transform into. And we know this because this is what we decided. But last time, we only had a 0 here, so it was easier. This time, we're in a superposition of 0 and 1, so we have to consider the whole thing. So instead, what we're going to do is set up a table here where we have x and f of x. And this is just what I decided to do. Again, Nielsen and Chang expect you to be able to do this. I couldn't do this by looking at it, so I did all the math. So now you get to watch me do all the math. So if this is obvious to you what the results are, I apologize. It was not so obvious to me. So x is going to have two values, 0 and 1. And f of x is going to have two values, 0 and 1. But we have to write all the permutations of them. So that's 4 permutations together. Right? So when x is 0, f of x is equal to 0. When x is 0, f of x is 1. When x is 1, f of x is equal to 0. And when x is 1, f of x is equal to 1. Okay? Now, this is going to have repercussions for the transformation. So we're going to say that I'm going to write this state here for each of these values. Okay? So again, it's 0 modulus 2 addition with f of x minus 1 modulus 2 addition with f of x. And of course, all of them are going to have a 1/2 out in front. So it's going to be 1 over the square root of 2. 1 over the square root of 2 out in front. But if the first result is, where is my end of the board? Oh, I'm way over there. Okay, I should be good. So if the first result, so if x is 0, okay? So we're going to have the first state be 0. So x is 0. So modulus, so let's do 0, 0, okay? So if x is 0 and f of x is 0, then it's going to be 0 plus 0 divided by 2 is going to be 0, okay? Good. 0 state. It's still a state. And then we have the minus, and then if f of x is 0, it's going to be 1 modulus 0, so it's still going to be 1. Good? Again, modulus 2 addition is basically you add these two numbers, divide by 2, and it's and if there's a remainder, then the answer is the remainder. So if it's 0 plus 0 divided by 2, it's just going to be 0 divided by 2 with a remainder of 0. If this is 1 plus 0, then it's 1 divided by 2, so there's a remainder of 1. Okay? That's how modulus 2 addition works. Now, that's at least how I understand it. Okay, so then what about 1 over the square root of 2? And this one, 0. But now it's a little bit different, right? We see that the first state, we have 0, but now our f of x is 1. So we have 0 plus 1 modulus 2 is 1. Right? And then the other one is subsequently 0. So can we rewrite that? Well, sure, let's rewrite that. So we're going to rewrite that with the minus out in front so we have the same exact state in the parentheses every time. So basically, I'm just going to pull the minus out here. And then this becomes 0, and this becomes 1. We get back to our original state. So we're going to do the same thing for this one and the last one too. Square root of 2, 1 this time for x. And then our state is 0 minus 1. Because again, we have our f of x is 0, so this side's going to stay the same. And then lastly, we have minus 1 over the square root of 2 times the 1 state times the 0 state minus the 1 state. Okay? That's what we get. So that's our table for setting all of this up. Okay? Again, this f of x is what we put down here, and then we do this modulus addition, and that becomes the states. And we found that this one and this one switches these states around, so we're going to pull out the minus here. So now this is what we get, okay? If we apply this, we have to consider all of the transformations that are possible. But that is a little bit of an issue, right? Because we don't know exactly what f of x is. But we can say about a relationship between f of x, between f of 0 and f of 1. So I'm going to erase this and come back to here because now we're just going to be worrying about what's over there. Okay? I write so big sometimes. I'm a big writing boy. So now, psi of 2. Psi of 2 is going to be the following way. What if the f of 0 and the f of 1 are equal? So an f of 0 is equal to f of 1. So that happens twice, right? When f of 0 is equal to f of 1 happens twice, right? When x is 0, f of 0 is 0. When x is 1, f of 1 is 0. And then it happens again for the 1s. Right here. Here and here. So what does that mean? Well, we can add them all together for that specific situation. Add them all together. Add them all together. And the total outcomes are going to be the following, right? 1 over square root of 2. Let's get some distinguishing lines here. 1 over root 2, excuse me, because there's 2 square roots of 2. So it's going to be 0 plus 1. I didn't give myself enough room, so I'm going to have to move that. And then 0 minus 1. Minus 1. There we go. Right? We have, for the x values of 0, so when x is 0, we have, the 0 minus 1. So that's good. And then when x is 1, we should have, again, we want them to be the same. So we'll have this, and then that should be, when x is 1, f of 1 should be 0, and then we want this one. So we just add those two together, and that signs a 1. Or a plus, excuse me. And then in the other term would basically be if f of 0 and f of 1 are not equal, because that's also a possibility. And this is going to make a lot of sense in a second. It might not make sense of why I'm doing this right now, but it will in a second. So this is when f of 0 is equal to f of 1, and this is when f of 0 is not equal to f of 1. And that should cover all 4 situations. So now we know we have covered all possible situations that we can concoct out of this arrangement. Okay? Because it's going to be the case that either f of 0 is equal to f of 1, or it's going to be the case that f of 0 is not equal to f of 1. What's the situation like that is? Well, what about 0, 0, and 1, 1. There we go. That's one situation. Then this would be the other one. The inside would be the other one. So there's all 4 possibilities. Now, that's right here. So we've gone through the transformation. That's the hard part. Then we're just going to send this one back through a Hadamard gate. This one back through a Hadamard gate. And then take an evaluation. Remember, this is still the first qubit, and this is still the second qubit. Okay? So the first qubit, remember the Hadamard gate has this unique thing where if you apply the Hadamard gate once and then apply it again, you get back to the original state. Right? So that's nice, right? If you apply a 0 to a Hadamard gate, you split it up into a superposition of states. But then if you apply the Hadamard gate again, you go right back to the 0 state. Okay? Which is nice. It's really handy. And it is even more handy in this situation because this means that we'll go back to 1 over the square root of 2, because now I have to pull another 1 over the square root of 2 out of these. But we'll have the 0 gate for the first one because this is a 0 gate. So we'll pull that out. So you go 0, hits the Hadamard, turns into this, hits the Hadamard again, 0. Excellente. And then this gate again. So we have the qubit again. 1, and then we have another plus or minus 1 over the square root of 2. Because this state is the 1 state. Bald clap. Welcome to the channel. Thank you for the follow. So this is the second. So this is a 1 state. So when you apply the Hadamard again, it goes back to the 1, and then we get 0 and 1. Now, here's the beauty of this. This is what we've been doing. This is the only reason we did all this nonsense. Okay? It's for the following statement to be true. That is, that if we have f of 0 equal to f of 1, we get 0. If we have f of 0 is not equal to f of 1, we get 1. That's it. That's the goal. This is, again, let's rewrite those down here just to keep those rules. And then f of 0 is not equal to f of 1, blah, 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 da, da, da. So otherwise we know that if f of 0 equals 1, we get this. If f of 0 does not equal 1, that's that. We didn't really do anything. We have not evaluated f. We've evaluated f 1 time, right? Alls we did was only evaluated 1 time, but we have now a relationship. F of 0 is equal to f of 1. Or f of 1 is equal, or f of 0 is not equal to f of 1. And all we had to do is take 1 measurement of 1 qubit, right? If we measured this qubit and we got 0, we know that f of 0 is equal to f of 1. If we measured this qubit and got 1, we measured this qubit and got 1 instead of 0 if we got 1. Then we know that f of 0 is f of 1. And it's always going to tell us one of these concretely, 100%. It's going to give us a 0 or a 1. It's not a random, this is not a random opportunity anymore. This is 100% definitely going to be the situation, depending on what we get from our measurement. So we do this quantum gate. We run 1 calculation of f of x, and we get we know a relationship we know a relationship between these two things. Whereas classically, you won't be able to tell any type of information, any type of relationship between the two of them unless you run two calculations. You need two calculations. So that's what parallel calculating means. Is all we have to do is set up this very weird and complicated quantum computer, but then the only classical computation we did was just measure this, and then we have a relationship that we did in half of the processes that it takes to do a classical computer. Now, this is really elaborate for a classical computation. You could say, I could just figure them out really quickly on a classical computer. Sure, but just imagine what you could do with this. That's the point. The point is like now you can take a function, you can spread it out over a bunch of qubits, right? So you take this f of x, spread it out over a bunch of qubits, and then run all sorts of calculations with it. And yeah, and then you can infer some relationships between that information without having to measure it at all. And then that's the goal. That's the key. That's the beauty of the quantum parallelism. So what we get is, and it looks kind of random, right? But again, it's not random. This is 100%. Why is this 100%? Because this is a consequence of the interference. And I don't really know 100% what that means. Other than, we know that all of this stuff works as, well, I won't even speculate. I'm not 100% sure what it means, but it is a property of interference. Maybe at some point in time we'll go over and kind of go into a more depth of what that means. But David Deutsche's paper explains it in detail, and the authors only kind of gave like an overview of it. But anyways, that's it. Quantum parallelism. What is a quantum computer good for? Lots of calculations running simultaneously.